Hi everyone. I don't know what's happening with the computer here, so it seems like I cannot do the slideshow, or else there's nothing playing here, so I will just do it this way. Hope you can see it clearly. And this is week 5, so you could see there are lots of things we want to do in the tutorial. The first one, I would say, maybe you would wish I'd do some review for a mid-test. And secondly, for the heat exchanger analysis, we need to do the second part, which is correction factor and NTU. But in the lecture, you haven't go to NTU yet. So this week, our practice is only on the correction factor, and we will do the NTU method next week. And the third one is, because next week you are going to do the heat exchanger lab, and you will need to write your lab report on that. So that starts on Tuesday for Group A and Thursday for Group B. So I have to explain some things about heat exchanger lab. So although I guess you would help me to go through from the review first and then to heat exchanger lab, but I will do this to explain something for heat exchanger lab first. Okay. So the heat exchanger lab would be a platform, look like this. This is the plate heat exchanger, and although we did prepared some materials for you, for example, to explain what this experiment setup consists of, what's the details of that, and also what's the steps for you to operate from the beginning to the end, then Kiao says he's pretty sure that you are not going to look at this guide beforehand. So that's why I think you could wait until Friday that we do some step-by-step operations and make a more simpler guide to you. So you can print it out and bring it Tuesday or Thursday, because we want everyone to have the hands-on experience on this one. Because you have all the things running here, but we are operating that through this user interface, so that's a software. So we would have everything set up for you. For example, where is the inlet temperature, outlet temperature for hot water and the cold water. But what we are going to do is basically like input what's the flow rate here, adjust it to a larger one or a smaller one, and then just click record. So everything will be recorded in the Excel sheet. So you could imagine it would be really boring if I do all the things for you. So that's why we hope everyone come to this session could like have a look at this, know what's the configuration, what is the parallel, what is counterflow, and have all the data ready for your own analysis. And also, because you know we have a very crowded lab space, so we hope that for Tuesday when Group A comes, you can come in the first half. So I think that might be 15 students maximum to do the practice, and then for the second half, another group number, like from 7 to 13. So it's labeled in your sign-up sheet. And the same for Group B. So when you come, so come in the first session or the second session, so it won't be too crowded. So, and the steps would be really simple. We are working on plate heat exchanger, which is this one. And when it was connected, you do the parallel flow and change the flow rates for 2 or 3 cases. And then you unplug these tubes and change it to counterflow, and also repeating all the measurements and do different flow rates. So you will have a set of data to analyze what's the difference between parallel and counterflow in terms of the effectiveness. And another way, another data we'll provide is a different type of heat exchanger, which is tube-in-tube. But because the setup is limited on this platform, so it's quite unnecessary that we change this plate exchanger to tube-in-tube heat exchanger, because all the other things would be quite similar. So what we are going to do is we only provide you some sample data for tube-in-tube heat exchanger. So in that way, your lab report should be analyzing the compare the effectiveness between parallel or counterflow, and changed flow rates according to your measurements, and also different structures, plate or tubing tube. So basically that's what we are going to do in the lab. And again, we are trying to organize a more simple guide to you. Hopefully it will be uploaded before Friday, but we will also send you an announcement so you can check where the documents are. So that's the plan for the heat exchanger lab next week. And then the practice for the second half of heat exchanger would be correction factor and NTU. And NTU will be explained in the next week. So this week, when we are doing the heat exchanger on correction factor, first thing is why we need the correction factor. So that would be basically because, for example, you have, I don't have a pen here. Let's try. Okay. So you would know if we have parallel flow would be flow is purely in parallel direction, or counterflow purely in different direction. But if you have a more complicated geometry, you cannot really tell it's purely parallel or purely counterflow. So that's why we need this correction factor for these more complicated geometries. And the calculation for those are really simple, because you will always be given an example of to have some correlations based on the constants of P and R. So you just calculate the constant P according to the inner tube outlet temperature, inlet temperature, and the shell inlet temperature minus the tube inlet temperature. So as long as you follow strictly according to the inner tube and the shell, and which is the inlet and which is outlet, you will have the value of P and R. So for example, if we have this configuration and you have smaller t in and t out and capital T in and t out, if you have the P calculated as 0.5, then you can find it from this line, and also find out what is your R value. So for example, R value is 1, so this should be your correction factor. And the correction factor F, you can just utilize in what you already know, the Q dot equals to UA delta T ln. So that's what we have practiced last week. So the correction factor is the only additional thing you need to include in this calculation. So I think for this one, the most common problems would be, maybe you know the heat transfer rate from thermodynamics, and you will be given with mass flow rate, temperature change or something. Sometimes we will need you to find out what's the total heat transfer surface area. Or sometimes we give you the surface area, but we want you to find out what's the overall heat transfer coefficient. Okay, so this part would be really simple, and we can do a practice based on this. So this is a shell into heat exchanger. I just realized I uploaded the wrong version of solution to Canvas. So currently no answers on Canvas, but I will replace that later. That should be this part. When you are looking for log mean temperature difference, you always follow which one is the 31 and the 32. So if it's parallel, you use hot inlet minus cold inlet. But in this case, you coming in and coming out. So generally, it would be a counterflow case. So delta T1 should always be the temperature difference on this side if you are going to calculate log mean temperature difference. And this part is delta T2.
all get the correct answer. The surface area should be 16. Have you finished your calculations? Does anyone need more time? No? Okay. So I guess because we have a more complicated structure, so it might look a little bit confusing about like shell inlet outlet, inner tube inlet outlet. So let's just start from the beginning, like what temperature should be the delta T1, delta T2 for PNR. So if we have a heat exchanger, it could be parallel or could be counterflow. So you will know if it's parallel, it looks like a different shape. That's something you are going to include in your lab report. Because in lab report, as I mentioned, you need to do both parallel and counterflow and do the calculations for that. So I provide this as an example, which is counterflow. So for counterflow, the first equation we need would be UA delta T. So if you are familiar with convection, you know it's just convective heat transfer, similar to HA delta T. But the difference is the heat transfer between the cold fluid and the hot fluid is very complicated. They are not a linear temperature difference. So the temperature difference, to be more accurately represented, should be in log mean temperature difference. But how you calculate this log mean temperature difference, it will always be given as, the information will probably be given as if it's parallel, what's the delta T1, and if it's counterflow, what's delta T2. But actually, if you do enough practice, then you will see you don't need to follow that. You just find where is your hot inlet. So this part should be your delta T1. You use hot inlet minus whatever here. And then the other side will be delta T2, and that is from hot outlet minus whatever here on the cold side. So once you get delta T1 and delta T2, these two will only be used to find out what is your log mean temperature difference, which is this one. So that's delta T1, delta T2, and delta T1 on delta T2. And so this delta T1, delta T2 is only for us to find out what's the log mean temperature difference. If we have a very simple geometry, that's the first part, and this part, heat transfer rate is from heat transfer. So that's convective heat transfer. But on the other side, we always need this energy balance. So on the other side, from thermodynamics, if you know the mass flow rate on either side, and you know the inlet and the exit temperature, so you can always find out what's the heat transfer rate. And these two should be equal. So we always use these two set of equations to find whatever we need. For example, this case, we want to find out what's your surface area. So we need thermodynamics first to find out what's the total heat transfer rate. And this is only on the water side. So here you have water outlet minus water inlet. But when it comes to heat transfer between these two fluids, you have to calculate log mean temperature difference first. So when you finish these two parts, if that's the simple geometry, you can just stop here. But as we mentioned, we have shell and tube heat exchanger. Although in this case, it looks like generally just according to the inlet and outlet direction, it could be considered as counterflow. But inside the tube, the flow directions are not purely counterflow. So that's why you need the correction factor to correct this type of heat exchanger. So when you are looking for F factor, you will always have chart and also this kind of schematic configuration. So in this figure, it says capital T would be the shell and little t would be the inner tube. But it will not necessarily all the same. So every time you need to pay attention which one is the shell and which one is the inner tube. So these two should match. That means for T value, you use the inner tube outlet and inlet, and shell inlet minus inner tube, whatever. Just to follow exactly how this chart says, so you get P and R, and that is your correction factor. So hope everyone could get the correct correction factor from this chart, and then you just utilize this simple formula to find out what's your surface area. So that's all we need to know about correction factor. And next week we're going to introduce the NTU method. But although it sounds like difficult, but actually very simple, as long as you just follow exactly what is presented here in the tables. Yeah. Any questions? No. Okay. So that's the solution. I will update the solution later. Okay, so I think we can come to a simple review about your midterm test. Okay, so I didn't prepare any slides on the review because, you know, we shouldn't do that. But it's just like we don't have too much things to explain in the tutorial this week. So I guess I just take some time to go through these slides and see if you get any specific questions. I can stop and explain all that things to you. But I would just claim that I won't be responsible for any consequences of this. So you shouldn't be expecting I'm talking about anything very close to the midterm test. But because this is just the lecture slides, so in the first part, we just take a review on this heat transfer, so advanced thermodynamics. So I guess this part, as long as you know what's the resistance and how to calculate the overall heat transfer coefficient, that's fine. And this is a formal start of our lecture. It's applied heat and mass transfer. So we should really go through all those slides about refrigerations. And you remember we spent lots of time explaining what the four components. So you should be able to tell what's the four components and how to calculate the heat transfer at each section. For example, evaporating section, that's cooling capacity, and compressor, that's a work input, and what's a part of condensation. So that's, we have done the practice, and you could remember that's purely like heat transfer rate would be m dot times delta H. So which delta H you are looking for would be each part of the heat transfer rates. And that part would be about calculation, but for concepts,
also want every student to know what's the curves on the pH diagram and TS diagram, because you must know how to reflect these 4 parts in the pH diagram or TS diagram. You can find what's the delta H here and complete all the following calculations. So in this part, not only on the pH diagram, but also you see we have provided so many curves that you need to understand. For example, pH diagram, the horizontal line would be constant pressure, but which one is the constant temperature? So that should be like vertical and go horizontal and go vertical again. So you need to get familiar with each section about that. And also, like in this section, you need to know how to convert this TS diagram and also convert between the pH diagram, something like that. And after this would be some analysis, because one most important thing about refrigeration is we want to know what's the coefficient of performance. So hope you still remember that we spent some time analyzing if which parameter changes, what's the influence on the COP value, because that's a very practical case you will need in the if you're going to do HVAC system analysis. So that would be also some part. So basically all the slides you should have a look at about all these values. And also paying attention to some details, like we started the analysis by using the vapor compression, which is the Carnot refrigeration cycle. What's the character of this one? And it would be a little bit different from the actual refrigeration cycles. So how do you connect these two, like the ideal Carnot refrigeration cycle and also another realistic refrigeration cycle? And also another case would be when you are doing your assignment, I think you will have the practice about calculating what's the actual entropy change, just to find out what's the actual enthalpy change based on the provided efficiency. So some students wrote to me by asking how to calculate this, so it's actually already provided in the slides. If you are doing your assignment, have some questions about this part, you can do some analysis according to this. So that's about refrigeration cycles. And the second one would be boiling and condensation. So if you go through these slides, then you will see we started the boiling part by, firstly, you need to know how to find the correct fluid properties from the tables and what is saturation temperature. And if you are given a pressure, how can you find or do the interpolation to find out the correct fluid properties? And then what is saturation temperature? When do you need the saturation temperature? That's about some basic concepts about boiling. And also for boiling, if we are doing calculations, then we know we have lots of empirical correlations provided to us. For example, this is the heat flux we use, the expression we use to calculate heat flux for nuclear boiling. And what is nuclear boiling? When should you use the equation for nuclear boiling? So you should always go back to the slides to look at the different stages, 4 or even we have 2 different ones in the nuclear boiling. So that is to help you, like all the explanations to help you understand the different regimes and select the correct correlation to find out the nuclear boiling. And another thing, I'm not sure if we have done the practice in the tutorial, I forgot, but you know this one is heat flux, right? And what we usually need the capital Q dot, which is the heat transfer rate. So you know you need a surface area to find out the total heat transfer rate by calculating heat flux first and times the surface area. That's your total heat transfer rate. And that kind of values might always be used to used with some other informations like the heat transfer equation for convection or the other thing, and or with the delta H one. So as long as you understand how to use these expressions, then it's fine. But the only thing we need to remind you is, I forgot which one, but okay, so that part is for boiling. But if you come to the condensation, you will see you need to consider a modified latent heat of vaporization. So we have mentioned this in the tutorials already. Under which circumstance you should consider subcooled, and under what circumstance you should consider superheated. And also some correlations, some heat transfer could also be calculated by utilizing mass flow rate times the latent heat of vaporization. And okay, so the only thing I need to remind you, I also did that in the tutorial, is if you want to calculate this HFG using HFG star using the fluid properties, then there would be two types of fluid properties. One is you use the film temperature to calculate all the liquid related fluid properties. So the film temperature should be the average of surface temperature and the vapor temperature, saturated vapor temperature. Because the film might be actually under the temperature of the average of these two. However, the only thing you need to, the only thing that's different is your HFG utilized in this formula should be found from the saturation temperature. So I believe I already explained this in the tutorial. So I guess it's fine just to remind you like this. So that's something we have students always make mistakes in for the calculation of condensation. Other than this, I think all the other calculations should be fine. So that's for condensation. So you could have a quick go through all those slides and pick a practice so that you could do the calculations. And also some other things, just small things, I also mentioned in the tutorials, because we have so many parameters to bring into calculation. For example, the HFG, in the table that they provided to you would be in kilojoules per kilograms. But some other parameters like heat capacity, they would be provided in a unit of joules per kilograms per Celsius degree. So you just make sure you are having the correct unit to be calculated. Otherwise, you might lose your score on the final results for that. So that's the boiling and condensation. And also the thermosiphon is included because thermosiphon is only a matter of combination of boiling and condensation. So you have another slide which I think Kiao already went through with you about all the calculations over heat pipes. So we would recommend you to go through all the calculations if you haven't done so, because you need to understand we have several parts, the evaporator parts, adiabatic region, and the condensation region. So everything introduced in this lab guide would be possible to be tested in your midterm test, because we have from step A to the final step, including the calculation on evaporating, condensation, and also to compare the thermal resistances in different parts. So if you go through all the calculations according to the lab guide provided, then I think that's fine for the midterm test part. So the midterm test will cover up to here, and the heat exchangers will not be tested. So that's all we have to review for this part. Do you get any questions?
Kiao, I think you sent out an email saying put up the formula sheet test. I could not find it when I did it.
Okay, I will double check that. I will upload that sheet with the solutions under this week, so you can have a check like 1 or 2 hours later. Okay. Any other questions? No? Okay, so that's all for the tutorial today, and all the best for your mid-test.